Hi everybody, this is lesson 2.3.2, and in this lesson, in the transformations chapter, we're going to take a look specifically at inverses. Now, inverses are a type of reflection, and although we did reflections in the last lesson, we're going to focus specifically on inverses in this one. Now, with inverses, it's important to remember that the inverse transformation swaps the independent and dependent variables in a function, or relation for that matter. And because it swaps the x and y variables essentially, all of the invariant points for this particular transformation are going to be on the line y equals x, because when you swap them, it's not going to make any difference. Additionally, I want you to be aware that this transformation is going to have an impact on both the domain and range of a function or relation. And in fact, it's going to swap the domain and range. And that's going to be one of the things that you're going to be expected to do, particularly on major exams, is identify that this is a transformation that will change both. Another thing that you're going to be expected to do is determine how to restrict the domain of the original function or relation so that its inverse is also a function. And that's actually what we're going to spend a fair bit of time looking at in this lesson. And you've probably already guessed that this is kind of a difficult thing to do, so please be careful when you're investigating the restrictions on the domain. So now let's take a look at an example. Given that the function f of x is equal to 3/4 of x minus 2, state the equation of its inverse together with the domain and range of the inverse. State the coordinates of the invariant points if they exist. Okay, well, to determine the inverse, you simply need to swap the independent and dependent variables like we said before, and then we solve for y if we can. So in this case, swapping the x and y variables gets us the equation here, x equals 3/4 of y minus 2. And now we'll start the procedure of solving for y by first adding 2 to both sides, so bringing it over so we get x plus 2 is equal to 3/4 of y. And then we'll multiply both sides of the equation by 4/3 to remove the coefficient, and we get that y is equal to 4/3 of x plus 2. So now based on that result, we see that the inverse is actually a linear function, and that means its domain is going to be an element of the reals, just like its range will also be an element of the reals. Okay, now to find the invariant points, what we're going to do here is we're going to take advantage of the property that invariant points are on the line y equals x. So what we're going to do is we're either going to go to the original equation or the inverse, and we're going to set the y equal to x. We're going to replace it with x and solve for that variable x. Now, probably going to want to work with the easier equation, and in this case, it's probably the original function. So we're going to get here that x is equal to 3/4 of x minus 2. Now we simply need to solve for x, and I'll start the process by getting the x terms together. So I'm going to bring the 3/4 to the left-hand side by making it x minus 3/4 x equals negative 2. And when we combine like terms, we get that 1/4 of x is equal to negative 2, which then allows us to get that final result that x is equal to negative 8. And since the invariant point is on the line y equals x, in other words, those 2 quarters are the same, we can conclude that the invariant point must be the point negative 8 comma negative 8. Okay, now our next example is going to push us in the direction of the big idea really in this chapter, in this lesson I should say. Which of the following restrictions on the domain of the illustrated function ensures that its inverse is a function? This is a multiple choice here. Either it's x is greater than or equal to 1, x is less than or equal to 2, x is greater than or less than or equal to 4, or x is less than or equal to 5. Now, it might not be 100% visible here on the graph, but the vertex of this parabola is the point positive 3, comma 2. Okay, now to really get what's going on in this question, you have to be extremely clear on the fact that an inverse swaps the horizontal and vertical properties of the graph. So, in other words, because the vertex is the point vertically where the graph changes direction, when you find the inverse of the parabola, you're going to get another vertex, but this time the vertex is going to represent the horizontal change in position of the graph. Now, as such, in order to ensure that the inverse of the parabola is a function, you can't have that turning point, that horizontal turning point. So you have to restrict the original domain so that you don't have both sides of the vertex. You can come right up to the vertex, right up to that turning point, but you can't include it if you want the inverse to be a function. So if you glance back at our choices here, the first choice is that x would be greater than or equal to 1. But because the vertex is at the point 3, 2, restricting the domain to being greater than or equal to 1 is actually going to include both sides of the vertex. Doesn't work. If you restrict the domain to be x is less than or equal to 2, that actually works because 2 is to the left of the vertex, and if I restrict the domain to all values less than that, I never actually include the vertex in that domain. I'm not including the turning point, therefore when I find the inverse, I won't be including that turning point either. C and D, less than 4, less than 5, they are both going to include the vertex, both sides of the vertex, so they wouldn't work. The answer is definitely B. So now let's look at another question, and we're going to do a little bit more with this one. Consider the function defined as f of x equals x plus 1 squared minus 4. So the first thing that we're asked to do is determine the equation of its inverse. And once again, you got to remember that finding the inverse is simply a matter of swapping the independent variables and solving for y, or the dependent variable. So in this particular problem, our first step will be to write x is equal to y plus 1 squared minus 4. And now to solve for y, our first step will be to bring the 4 over by adding it. So we'll get x plus 4 is equal to y plus 1 squared. And then everyone, I know that for a lot of people it is very tempting to want to expand out that y plus 1 squared. But really, I encourage you, take the square root of both sides instead. This is a much more direct way to the answer here. Just remember that when you take the square root in a case like this, you're going to get plus or minus the square root of x plus 4 is equal to y plus 1. And then you bring the 1 over to solve for y, so that y is equal to negative 1 plus or minus the square root of x plus 4. Now the next question asks us to find the restriction on the domain that ensures that the inverse is also a function. Because in this case, it's not. The inverse isn't. As soon as you have that plus or minus in there, the result is going to be something that's a relation, not specifically a function. And you know what? In this particular case here, it will probably help if you had a sketch of the original function so you can really see what's going on. So here's the original function. I'm sorry, the graph goes slightly off the screen there, but you can see what you need to see here. Notice it's a parabola that opens up with a vertex at negative 1, negative 4. And so let's step back a bit. And as I said, it's a parabola with a vertex of negative 1, negative 4. Now, based on work that we did just a little while ago, we know that if we want the inverse to be a function, we cannot include the vertex. Or at least we can't include both sides of the vertex. We can come right up to it, but we can't include both sides because that vertical turning point will then become a horizontal turning point, and we can't have that if we want to have a function. So now we got to consider what we're doing here because we're not given any indication as to how to cut this. So if we cut the original domain at the point where x equals a, then you got to make a decision based on that value of a. And now I know introducing a new variable is kind of making this more complicated, but you actually really need this new variable in order to make sense of this. We're going to cut and restrict the domain based on this value a. If a is greater than or equal to negative 1, meaning that the value of a is to the right of the vertex, then we need to restrict the domain to the right of a. We need to keep going so that we move away from the vertex. So our whatever the value of a is, as long as it's greater than negative 1, the restricted domain has to be x is greater than or equal to a. On the other hand, if we choose a value of a that is less than or equal to negative 1, so it's possibly to the left of the vertex, then we must restrict the domain such that its x is less than or equal to a, or it continues to the left, moving away from the vertex so that we don't include that turning point. So the domain would have to be then, as long as x is a value less than negative 1, the domain would be x is less than or equal to a.